recording this, so people who don't come, which as of right now, it looks like a lot of people will get to see it later. Okay, so like I said, I'm just gonna go over worksheet 17 since I didn't get a chance to do anything with alkynes at the beginning. Oh, sorry. After you guys covered it, so yeah, that's what I'm gonna do first, and then I'm just gonna go over everything from chapter 5 to your most recent stuff. I have a sort of script, I guess I'll post it online afterwards, but yeah, I'm just gonna start with the worksheet. Okay, so the first problem is naming alkynes. Just like with alkanes, and you guys probably covered this in class, but like we give the higher priority for numbering to the multiple bond, so the triple bond here. We care more about that than any substituents. So if we started numbering from here, the methyl group would get number 2, but that would give the alkyne number 4 compared to giving it number 3 if we start from over here. So we start from the left to give that your priority. And this is a carbon and this is a carbon, so you have to count your carbons carefully there. So we have a methyl, carbon 6, so it's 6-methyl. And then just like with alkanes, we can name this one of 2 ways. I guess I'll show both. There's 7 carbons, so it's heptyne. Or you could say 6-methyl and then hept free line, putting the free in between to show that that's a double bond. And naming it the second way kind of works better if there's like a triple bond and a double bond, because then I'll just make something up, I guess. So like this, I'm just gonna name this on the spot. See, there's a triple bond at carbon 1 and a double bond at carbon 3, so it's pent. There's 5 carbons, so I guess I'd name this pent 3 ene 1 ine. So like there you can see the 3 is relating to the double bond and the 1 is relating to the triple bond. So naming it like this just makes it easier. But if there's just a triple bond or a double bond, I think doing it this way is easier. But whatever works for you, that's just my recommendation. Okay. And the second part for number 1. Again, we could start numbering from over here to give the methyl group number 2, but that would give the triple bond number 3. So we're going to start numbering from the triple bond. So it's going to be free methyl. It's 6 carbons long, so it's butene. I mean, it would be butane, but it's butane, and the triple bond is at carbon 1, so it's 1 butane. Okay. I'm going through this quickly because naming is something you guys have done a lot, so I'm assuming you're comfortable at this point. But if there are any questions, you can stop me. Okay, so we could either start numbering from the left or the right, and top or bottom on left and right is the same because of symmetry. But we're going to want to start to number from the left because that'll give the first substituent, like it'll put the first substituent on carbon number 2. And it'll also put the triple bond at carbon 3 instead of starting over here where the first substituent would be at carbon 3 and the triple bond would be at carbon 4. So like the substituent and the triple bond back each other up in this case. I think it's a good idea to check both directions just to make sure you're correct, even if you're pretty sure you're correct with your numbering. Okay, so there's an ethyl group here at carbon 5. and then there's a methyl group like carbon-2. Those are the substituents, and we do stuff alphabetically, so it's going to be 5-ethyl, 2-methyl. It's 7 carbons long, so we have hept again, and then the triple bond is at carbon-free, so we put a free, and then line. Oh, I did it that way. Well, either way works, but this is how I use this one. Or you could say heptime like this. Okay. So that's number 1. Number 2, I'm giving you substrates and reagents, and we're trying to figure out what the product is. Do you need a dash between the methyl and hept? I'll go back. Shoot, that's really far back. Okay, sorry, I didn't see. So I named it, do you need a dash between the methyl and hept? I'll write the name again. I'll abbreviate it, and so this is one way you could name it. And the other way you could like have the 5-ethyl and the 2-methyl, and then you put hept. So you have like, can you do free methyl hept free? Oh, do you need a dash between the methyl and the hept? Yeah. Oh, it would be 2-methyl hept freeine if you do it that way. And I think what you're saying there is correct. Sorry, I didn't understand. I had to write it to understand, but I'm pretty sure what you're saying is correct. Just, I think it's safer to put the dash between the methyl in there, just because, like, for me personally, it makes it easier to follow what I'm doing. I don't know if there's a set rule for it, but I never got marked down for doing it the way that I've been showing you guys, so I'm kind of just sticking with it. Okay. So when we're looking at alkyne reactions, one thing that I think is good to either write down actually or make in a mental note is like look at the triple bond and identify if it's terminal or internal, because for some of the reactions that's pretty important. I mean, for this particular one, it's not really, but I still think it's a good practice. So what kind of triple bond is this? Is it internal or terminal? Yeah, it's internal, because if it was terminal, it would be at the end of the chain. So it would have to be like here or here on the left or right. So internal. And then we have H2 and palladium carbon catalyst. So what is this going to do to the triple bond? It's something that you guys have seen before with alkenes. But it's just going to reduce it, add hydrogens. So you just get an alkane. And I don't think you can really talk about stereochemistry here, but I'm assuming they'd be cis to each other. So you just have like a bunch of dashes or a bunch of wedges for all the hydrogens added, but it completely reduces the triple bonds. That's what H2 and the palladium catalysts do, or the platinum catalyst. And for part B, it's the same substrate, but a different reagent. Do you guys know what H2 and Lindlar's catalysts do to an alkene? No, the product here. Yeah, it forms a cis alkene, so it partially reduces the triple bond. It doesn't go all the way to an alkene, it just goes down to an alkene, and it specifically forms a cis alkene. There's another way to reduce alkynes and form a trans alkene, but this is cis, so cis or Z alkene. Okay, so that's the first two. What kind of triple bond is this? Is it terminal or internal? Yep, it's terminal because we have the alkene and the alkyne at the end of the chain. So when it's terminal, there's a chance for regioselectivity because like the spot on the right here is primary compared to the spot on the left being secondary. So like there's a potential for reactions that have regioselectivity to show it. Whereas for internal, both of them are secondary, so there's not going to be any regioselectivity. So like you'll see Markovnikov come up with certain reactions if it's terminal, but not with internal. Yeah. And do you guys know what this set of reagents will do to a terminal alkyne? Hydration, yeah, it's going to add oxygen and some H's. Yeah, I don't have the intermediate written on my answer key. That's the intermediate. Yeah, that's the intermediate. So it's good you guys know that. That might come up in some sort of multiple choice question, but the final product is what's most important. Unless he didn't tell you, what that wouldn't make a lot of sense. So it ends up forming a carbonyl, and it puts the carbonyl on the Markovnikov position. So there's another way, which is the next problem, to add the carbonyl. And I'll just go ahead and put that on the same page. I mean, both of you are correct. Like I said, the ketoenol is an intermediate. This is just the final product. So this is BH3 and THF with H2O2 and base. And while the reaction in part C put the carbonyl on the Markovnikov position, this is going to put the carbonyl on the anti-Markovnikov position, which is here at the end of the chain. And because it put the carbonyl at the end of the chain, it forms an aldehyde. So this formed an aldehyde. And this formed a methyl ketone. And it's a methyl ketone because there's a ketone and there's a methyl group on the right side. That's why they call it a methyl ketone. So, shoot. So yeah, this set of reagents here is the exact same one you guys saw with the alkanes, adding an alcohol to the anti-Markovnikov position, and it does the same general thing with an alkyne. It adds, instead of an alcohol, a carbonyl, but it adds it to the anti-Markovnikov position. If we did these two reactions with this internal alkyne or any other internal, it would just put the carbonyl on both carbons because there's no selectivity. So it doesn't matter which one you use with it, internal or with terminal, there is a difference, and it's important to recognize that. Okay. And what kind of alkyne is this? The triple bond is at the end of a chain, so it is terminal. So if there's regioselectivity there, like it'll show with a terminal alkyne, and that was supposed to be a Q. I didn't draw that very well. So we're adding one equivalent of HBr. If you didn't write 1 or 2, you'd probably assume that there's 2, but he's probably going to tell you explicitly. So if we added one equivalent, well, we can only add one, but like if we added HBr to an alkene, that would just lead to this. It leads to the Markov-Nikov addition of the halogen. So we get the same thing with an alkyne. You could probably draw out a mechanism for this. It would look basically the same as the alkene, but I'm just gonna go ahead and skip on that. Just draw the product. So the Br goes on a Markov-Nikov position, and then if you want, you can put that we added the hydrogen here. Like this is the hydrogen we added from HBr, and then the bromine got added to the Markov-Nikov position. And yeah, that's just that. It's the same exact reaction with the same selectivity that we saw with alkenes. And this is an internal alkyne because it's within the chain. Just like when we added Cl2 to an alkene, we're just adding 2 chlorines, and it's going to be added with trans stereochemistry, like they're going to be opposite of each other. Just like when we added to a double bond, I'll just say Cl2 again. They were trans to each other. They're also trans here in the double bond product. And if we added 2 equivalents, then there wouldn't be a stereochemistry, and we just have 2 chlorines on both carbons, but that's not something I'm showing here. If I'm going too quickly, please feel free to stop me, but a lot of these are things we've seen before in another form. That's part of why I'm kind of speeding through it. I'm also going to repeat myself with the review later, so yeah, that's another reason. Okay. So if this was, well, I'm gonna here. So this carbon here on the left side of the triple bond is bonded to another alkane. It doesn't have any hydrogens, but this carbon here on the right is bonded to a hydrogen. And that hydrogen isn't super acidic, but it is somewhat acidic. So basically this hydrogen could be taken away, this carbon could be deprotonated. And NH2, one of the reagents, is a fairly strong base. So like this first step, number 1, is just deprotonating that carbon. So we'll just draw the intermediates. And then the sodium kind of goes with the carbon with the negative charge. And it also forms NH3 because the hydrogen went to the NH2. And the second step, adding the CH3 Cl. So this is something you guys know, like an alkyl halide can act as a nucleophile or an electrophile because of this dipole. And we have a nucleophile here because of the negative charge, so it attacks the carbon and there's a bond to the chlorine that breaks. And I don't think you have to know this mechanism, but if you were confused as to why these steps lead to the product that forms, this is just a way that you can like draw it to show your work and explain to yourself why it is what it is. So this is the product because we took this carbanion and we like reacted it with the alkyl halide, so we just added this carbon to the chain. So something that is very good to do is like making sure you count your carbons. We had 4 carbons on the left. We added 1 carbon with the alkyl halide. And we have 5 over here, so we added 1. We didn't draw too many in the product, so we're good. That's just a good practice to maintain, because it's kind of easy to miscount the carbons in the triple bond and then add too many or something. So that's just my recommendation. Okay. This triple bond is at the end of a chain, so it is terminal. And this time we're adding 2 equivalents of hydrochloric acid. So the first equivalent, I'll go ahead and draw it. It'll be similar to the reaction we went over before. It's going to add a chlorine here and a hydrogen here. So that's what one equivalent does. And then the second equivalent, we'll just put another chlorine on that Markovnikov position and then another hydrogen on the anti-Markovnikov position. And you don't really have to draw the hydrogen, but I'm just showing that's what was added. These two are what's important. And there's no stereochemistry or anything, it's just they were added to the Markovnikov position. If it was internal, then it would be added to both, but they'd both probably add to the same carbon. It just, there'd be a mixture of products. Okay, so that's number 3. Doesn't seem like you guys have questions, so that's good, hopefully. All right. Can any of you tell me the reagents we'd use to get from this first step to the second step? And then this. Yep, that's the first step here. To deprotonate the, yeah. And then the second step, it could be CH3Cl or CH3Br. Those two work fine because we're adding 1 carbon and we added 1 carbon here. So first step deprotonates, second step adds a carbon. And then to get from 2 to 3, what would we have to do? So we're going from a triple bond to a double bond. And specifically, we have a cis double bond because this is the higher priority on the right and this is the higher priority on the left. They're pointing in the same direction. So we have a cis alkene. So yeah, H2 and Lindlar's catalyst. That's what leads to a cis double bond, like we have here. And then we're going and doing a reaction with this alkene we formed to form a cyclopropane, because we have that triangle over here. Do you guys remember the reaction to form that from an alkene? That's okay. Something that is kind of random, not really related to cyclooctane, but it's still something to memorize, so flashcards will help. Yeah. CH2I2 and zinc copper with some ether solvent. But I think like this part here is what's important. The CH2I2 and the zinc copper will form a cyclopropane from a double bond. So that's that last step. And yeah, that's number 3. It's just filling in the blanks in a sort of synthesis problem. I think that's as complicated as synthesis could get with a test being taken online. So yeah, right. Okay, so can anybody tell me what's wrong with this reaction? There's 2 things. Too many carbons added, yeah. So like I was saying with one of the problems earlier, what we can do is count the carbons in a reactant. So we have 5 over here, and we have did I misdraw that? 1, oh, okay. No, I'm just not counting correctly. That's my bad. Oh, okay. I'll just erase those numbers. So there's 4 here, 5, 6, 7, 8. And with the reagents, we have 2 carbons added. So we went from 4, we added 2, and we should have ended up with 6 carbons. Wait, no, we had 5 at the beginning and we added 2, so we should have ended up with 7, but we have 8, so we drew the wrong product. So there's 2 ways you could theoretically fix this. You could fix it by just fixing the reagents. So we started with the same substrate, but we want to get that product, so we would just rewrite the reagents. First step is the same, you're just deprotonating, but now we want to add free carbons, so it's going to be CH3, CH2, CH2, Br, because now we have free here being added. That'll add a propyl group. So that would be fine. Or we could fix the product that we draw. So I'm going to draw it over here, I guess, but so the left side has to stay the same. And we have 4 over here. Well, 5 total, so 6, 7. Now it's correct. So just count your carbons. That's the main takeaway I was trying to go for here. And I don't think this will come up as a question on your test, but it's just a sort of lesson I'm trying to teach you guys because it's something a lot of people mess up when they're doing reactions to add carbons. Okay, so that was worksheet 17. Now I'm going to go over a bunch of notes I made for everything you guys have covered since the first exam. I'm going to start with chapter 5 and just go in chronological order. So I'm not going to go over much practice. I'm just going to throw the topics out and what I think is important. So first, like chiral carbons, like being able to identify them, when a carbon can be chiral, when it can't be chiral. So like in order for a carbon to potentially be chiral, it has to be tetrahedral. So that means sp3 hybridized. That means no multiple bonds, no pi bonds. So that's like a first criteria you should look for if you see a double or triple bonds. Just count those out when you're asked to identify chiral carbons. And then in order for it to be chiral, after you recognize that it's tetrahedral, you have to see that it has 4 different substituents. So like this here has 2 hydrogens, even though the other 2 substituents are different. So because there's 2 hydrogens, it's not chiral. Like just the biggest trick in terms of making things look like a chiral center, but there aren't, is we don't draw the hydrogens in, but they're there, so you have to identify that. So that's really all I'm going to say about that. If you have any particular questions about a topic, you can like ask me, but otherwise I'm kind of just going to zoom through my general big tips on these, I guess. So that's just identifying chirality centers. And then like once you've identified that something is chiral, you should understand the concept of optical activity. You don't really have to know a whole lot about this, but you should just know that like if a molecule overall is chiral, and a molecule can have chiral centers but be achiral, that's a meso compound. But if the molecule overall is chiral, so if the molecule is chiral, then it will rotate plane polarized light. That's something that you need a special machine to help you identify, but you just have to know that if it's chiral, it will rotate plane polarized light. I could see that coming up in like a true-false question or something. It's just a conceptual, do you know what optical activity is kind of question. So I'm going to throw a lot of stuff that you might not need to know out, but the more you know, then the better chances you have. Okay, so the Conning-Gold-Prelog rules for ranking substituents, those are things that you really have to get down. So there are 3 rules that I kind of just copied and pasted from the book. I'm gonna try to summarize them. So number 1 is like, look at the atoms directly bonded to chiral center. And then rank them based on their atomic number. based on atomic number. It's supposed to be. And then guess I'll just move all of this up. That's not gonna work. Whatever, okay. If you can't distinguish some substituents just based on the first thing bonded, then you basically just keep going until you can find the difference. So keep going down the linear sequence of bonds. But I'm just going to keep going until a difference is found and then go back to number one. I could go over an example if you guys want, but this is something we've done so many times. I'm just throwing the topic out there. And I'm gonna erase the first two because I don't have enough space on this tiny whiteboard. Probably should have just erased the whole board, but I'm committed. Okay. That would have been faster. All right. Number 3. Multiple bonded atoms are equivalent to the same number of single bonded atoms. So, like, if we have a carbonyl like this, we could say that that's equivalent to this carbon here being bonded to 2 different oxygens, being singly bonded to 2 different oxygens, and then one of those oxygens is double bonded to a carbon. So you could draw it like this. You don't have to do this drawing, but it's a way of counting the bonds if you're trying to distinguish 2 substituents. And that's something I've gone over a lot of times, so hopefully you guys remember that. Just know how to assign RNS configuration. So what you have to do when you're doing that is put substituent number 4 in the back. And then draw an arrow from 1 to 2 to 3. If it's clockwise, it's R. If it's counterclockwise, it's S. And yeah, that's the safest way to do it. The other way is that sheet I told you guys about, just if number 4 isn't in the back. Then just draw the arrow. From 1 to 2 to 3. And flip what it looks like. I don't know how else to word that, but just flip. And I guess I will do an example for this, because it's hard to put it into words, but yeah, those are like the general notes there. Like I said, I'm going to be posting this, so if you can't keep up with my writing, then you can always look back later. But yeah, okay. So I'll just draw some generic SP-free thing. I'm not gonna come up with substituents. I'm just gonna give numbers for the positions. So number 4 is not in the back. So we could either rotate the molecule to make number 4 in the back, or just draw the arrow from 1 to 2 to 3 and flip what it looks like I was saying. So if we do this, it's going counterclockwise, so it looks like it's S. But because the 4 is not in the back, we flip it, so it's actually R. And I can show you guys that it's R by, like, we can take this bond here and just rotate around it. I didn't draw that arrow going in the right direction, but I'm just going to rotate around this bond to make the 4th substituent go towards the back. So 4 will go here, 2 will go here, and 3 will go here, and 1 stays in the same spot. And then when you draw the arrow, you see that it's R, so I recommend doing this rotation to check your work, but if you're crunched for time, you can resort to this cheating, and it'll probably work most of the time. I just recommend doing this second way if you have time, because unless you do something wrong with the rotation, it never fails. It's always correct. Okay, you should know about the different isomers and like how they're distinguished from each other. So this is definitely going to take up more than one page, but I'm just going to start with like naming them. We have enantiomers. What if 4 is a line? Okay, I'll go back. So I'm guessing you're referring to something like this when it's not on a dash or a wedge. It's the same idea as when we had 4 where 3 is right now. Like, it's not in the front, but the point is number 4 isn't in the back. It's in the back if it's on a dash. So because it's not in the back, we do like one of two things. We'd either look at it as it is. This looks like it's S again, so it's R. Or we could rotate around this bond. So I'll do that quickly again. So because we're rotating around the top bond, 1 is going to stay where it is. 4 goes to the back, 2 goes here, and 3 goes here. That should have worked. But that's part of why I say to check by rotating, because for some reason that didn't work here, doing the shortcut. So unless I did that wrong, but it doesn't look like it rotated incorrectly. So like I made these examples up off the top of my head. That's why it's not being perfect, but I would just recommend sticking to rotating around the bond. And I don't have models I can show you guys, but I'm hoping you understand that like I'm just taking this bond here and I'm rotating in this direction. So 4 goes over here, 2 goes over here, and 3 goes over here. What's important is 4 goes towards the back, and then we have this configuration where we can just draw the arrow like normal and identify it. So hopefully that answers your question. Well, it just led to more confusion probably, but hopefully you understand that you should always check your work if you're using a shortcut, if you can. Okay. So isomers, we have enantiomers, diastereomers, and chat box is blocking me. I'll rewrite that. So enantiomers, diastereomers, and meso compounds are all the things that were introduced in chapter 5. And we can distinguish between different isomers in a couple different ways. So first, enantiomers are non-superimposable mirror images. That's their definition. I guess we'll put a caret here. Non-superimposable mirror images. And an enantiomer has opposite configuration at every chiral center. So I'm not going to draw a molecule, but for example, if we had a molecule with like R and S configuration at its 3 different chiral centers, then an enantiomer, like its enantiomer would have S, and R. That's just some example. Like obviously, if it was a molecule, you'd have to look at the 2 molecules are given and identify these things. But just as an example, it flips at every chiral center. If it flipped at just one of them and then the other 2 stayed the same, then it would be a diastereomer, which I'll get to in a bit, but that's just enantiomers. I'm gonna clear the board. So I'm still talking about enantiomers. A pair of enantiomers have the same chemical properties. Like melting point, boiling point, solubility, probably other stuff, but just like they have the same chemical properties. They look like they're exactly the same way if you're trying to distinguish them based on that. So the only way we can distinguish between a pair of diastereomers is by their optical activity, by their rotation of plane polarized light. So I don't know, like this is something you have to find experimentally. It's not something you can be like, oh, this enantiomer had R configuration and this one has S, so this one is going to rotate it. Is going to rotate plane polarized light clockwise, which would be D, or counterclockwise, which would be L. Like it doesn't work like that all the time. You can't guess just, it means that you can't guess just based on configuration. It's something you find experimentally. But like in terms of a question he might ask something like, this molecule rotated plane polarized light in this direction and then this one rotated it in this direction. So what are these 2? Like enantiomers, diastereomers, or meso, and he'd say they're enantiomers because they rotated light in opposite directions. Just like that's another conceptual question that might come up. That's why I'm telling you all this. So that's everything I have on enantiomers. For diastereomers, their definition is stereoisomers that aren't mirror images. So, like I said before, they will probably have like just for example, going back to that same example, we could say like if the original molecule has RRS configuration, and then the diastereomer might have like RSS. So these two stay the same, but this one changed, so it's not a mirror image, but it's not the same molecule because it changed a little bit. So that would be a diastereomer. So it's same configuration, it's some chiral centers, but different at others. It's not different at all of them. It's not the same at all of them. I'm not going to try to put that in words, but that's just how you identify them. And so I guess a little note is a molecule has to have, so we must have at least 2 chiral centers to have a diastereomer. Which isn't super rare, so I wouldn't recommend like memorizing this little fact, but just like if there's only one chiral center in a molecule and you're given 2 things that could potentially be isomers, it can't be a diastereomer because there's only one chiral center. So I think that's just more important to be able to recognize than to memorize as a sort of fact. Okay, I'm gonna erase this because I'm running out of space. But I'm gonna abbreviate diastereomers. Cis and trans isomers are diastereomers. That's something you guys saw in the past that came up on your first exam, because like if we have this versus this, like the wedge stayed the same for chlorine in both of them, and then the dash for dimethyl changed from a dash to a wedge. So one thing stayed the same, the other changed. So that is a diastereomer. That's just like you weren't given that term before, but I'm showing you guys that you saw it before, and there's just a more correct term for it. And then also more recently, like C versus E alkenes are also diastereomers, which is also cis and trans just for alkenes. So if he throws like molecules like this or cis and trans at you and asks what kinds of isomers are these, then they both fall under the category of diastereomers. So that's just something to recognize. And then a pair of diastereomers have different chemical properties. So they can be distinguished by melting point, boiling point, solubility, other stuff. We don't have to rely on optical activity to figure out if 2 things are diastereomers. So they probably have the same bonding order like these 2 cycloalkanes here, but they'd have different stereochemistry, and we could distinguish them by like solubility or something. So another possible conceptual question. And then the last kind of isomer that came up in this chapter was meso compounds. It's not a very good looking S. So a definition for meso compounds is they have chiral centers but are achiral overall. I'm gonna erase that because I'm butchering it. Achiral overall due to internal symmetry, or due to symmetry in the molecule. So I will give an example of this when I finish doing the talking points, but that's just the definition. There are chiral centers, but the molecule's achiral due to internal symmetry. And they are generally given to you in a way that make them look like enantiomers, but it's just the same molecule given in a different perspective. So like, while enantiomers and diastereomers occur in pairs, meso compounds don't. So meso compounds are individual things. Like, we have two enantiomers or two diastereomers in relation to each other, but one meso compound is one thing by itself. There is no mirror image or other isomer. Okay, so yeah, I'm gonna erase the board. So still talking about meso compounds. Because they're achiral overall, they don't rotate plane polarized light. So again, potential conceptual question. And in terms of an example, it could be given something like this. So this is a chiral center and this is a chiral center. Does meso have symmetry planes? Yeah, they do. That is what I covered in the definition. They have chiral centers, but they're achiral overall due to symmetry. And symmetry planes is the kind of symmetry we're looking for. So like with this molecule, even though both these carbons that I circled are chiral centers, the molecule is achiral because we have this mirror plane here. So like if we reflected this chlorine to the other side of the mirror, it would go to that chlorine. And they're both on wedges, so there is symmetry. I could also draw it like this. And you might think at first glance that that's an enantiomer because we flipped the configuration. They both have the chiral centers from wedges to dashes, but again, there's this internal mirror plane. So because of that mirror plane and the fact that it's a meso compound, we could take this molecule and just like, it's hard to show with just a pen, but like flip it 180 degrees basically. So then the dashes would become wedges and the chlorines would be in the same spots and it would be the same molecule. So that goes back to that point that they're individual things, even though they look like they're not, like it's just one molecule. There are a lot of potential examples for meso compounds, but I'm not going to go over everything today. I'm just giving you one example here. Okay. And the last thing from chapter 5 is racemates or racemic mixtures. So racemic mixtures. And they are 50-50 mixtures of a pair of enantiomers. So because there's an equal amount of both enantiomers, they're going to rotate plane polarized light in opposite directions equally. So they rotate light in opposite directions equally. Just going to abbreviate that. So the rotation basically cancels out. And because the rotation cancels out, then you would say that the racemate, I'm gonna go ahead and erase this, but so racemic mixtures are optically inactive. Because they rotate plane polarized light in opposite directions equally. So like one enantiomer would probably rotate it clockwise, would be V. The other one would be counterclockwise, so L. So 50% is going this way, the other 50% is going that way. So they just cancel each other out and you don't see any rotation. So yeah, that's just another little conceptual thing that might come up. Okay, that was everything from chapter 5. Chapter 6 was just like an introduction to reactions. I'm just gonna go over some brief things. In general, you should just be able to draw electron flow arrows. I partly used the study guide I posted online to put this together, but it's still good to hear multiple times. Just to be able to draw the electron flow arrows for both polar and radical reactions. Polar reactions are what we've been seeing a lot of. It's just like nucleophiles and electrophiles reacting with each other. So like the alkenes and alkynes reacting and the alkyl halide stuff, all those more regular things. And then radicals are just like just a single electron reacting with something else. And then you draw an arrow like this with just a single head. Like that's what radical reactions are. And you should be able to do both if you're given like a set of reactants and some products. You should be able to show how the electrons flowed to get from the reactants to the products. And in terms of radical reactions, I'm gonna go ahead and erase this, but you should be able to identify the free phases of the reaction. So there's initiation, which is just like you start with no radicals and you form radicals. And how radicals are formed depends on the reaction, but light is used pretty commonly. So like you might have Cl2, and then this is just light energy coming in, and that would break the bond and form two chlorine radicals. That's just one example of an initiation step. You might throw something else at you, but the point is if you start with no radicals in the reactants and you end up with radicals in the products, that's an initiation step. And you should be able to draw those arrows to show how the radicals formed, which in that case was just breaking the bond equally. And then there's propagation, where the reactants have one radical and one non-radical species. And products lead to new radical species forming. So products have a new radical species. So basically the radical propagates. It is what it sounds like. I can give an example, but I've gone over a lot on my worksheets, so you can always look back at those or to textbook or notes, but that's just propagation put into words. And then still talking about radicals, the last step is termination. So for termination, the reactants have to where's where to put this? Okay. Sorry, I'm trying to wrestle with the chat box. So the reactants have two radical species. And that combine, so the two radical species combine. And products have no radical species because of that combination. So basically the radical terminated. It does what it sounds like it does. They just combine and there are no radicals in the product. So again, I could go over an example, but I've gone over a lot in the past. So that's just, let's put into words. You should be able to identify the nucleophile and electrophile in a polar reaction. I won't write that down, but just that's a thing you should be able to do, and we've been doing it a lot in the past. So it's the same as identifying loose acids and bases. Just know that like if something has a positive charge, it is electron deficient, so it's going to be an electrophile like all the time. And phile means loving in Greek, so electrophiles love electrons. That's how you can remember that. And then if something is negative, it's going to be a nucleophile. And again, phile means loving, and nucleo is referring to the nucleus, which has protons, which are positives. And nucleophiles love positive charge. That's why like they're negative and they're attracted to a positive charge. And if we don't have straight up charges, there's also dipoles like this between carbon and not very electronegative thing versus chlorine, an electronegative thing. So when there's dipoles, that's my bad. When there are dipoles, the electronegative side becomes partial negative and the non-electronegative side becomes partial positive. So this would be an electrophile because it's electron deficient due to that positive charge, and then this would be a nucleophile because it has a partial negative charge. So you should just be able to recognize within a molecule you might never have seen before, like what is a nucleophile and what's an electrophile. And you should be able to interpret those reaction coordinate diagrams. So what I'm referring to is something like this with energy on the y-axis and I guess progress on the x-axis. These could be given to you in a variety of ways. I'm just gonna make something up off the top of my head. Something like this is one form you could be given. So you should be able to identify, well, a lot of them will look more complicated than this, and I can come up with something more complicated, but in general, you should be able to identify the reactants, which is where the reaction starts over here on the left, products where the reaction ends on the right. You should be able to identify any transition state, which is like at the top of an energy barrier, like up here. This is a transition state. If we had something like this, like where there's two top of the hill spots, sort of like in between those two, like this is still the reactants and this is the products, and this isn't a good representation, but this would be intermediate in between the two slopes. So those are like the different species that you can identify from these. I'm going to erase this intermediate thing. So those are the species, and you can also sort of tease out the Gibbs free energy change from a reaction, or at least like determine if it's negative or positive, and then also determine the activation energy. So you can draw a horizontal line starting from the reactants, and then the energy difference, which is the difference on the y-axis from the reactants to the products, is called delta G, and that's the Gibbs free energy change. So Gibbs free energy change. And if this is negative, then that means that the reaction was spontaneous. And if it's positive, then it's not spontaneous. And spontaneity just means like, will the reaction occur without putting in a bunch of energy? If it's negative, then yes, it will happen. So that's like the thermodynamics of the reaction. So that tells you if it'll happen, but it doesn't tell you anything about how fast it'll happen. Like delta G could be a crazy negative number, which means it's definitely going to happen, but it might take a really long time. And how we can sort of quantify how fast the reaction is with the activation energy, which is the difference between the reactants and the highest slope, or like the highest peak in the diagram, which there's only one here, so it would be this. So the symbol for this is the delta, I think delta G dagger, or just say it's activation energy. And that tells us about kinetics, which is how fast the reaction goes. So the taller the difference between the reactants and the transition state, the higher the activation energy is, which you could think of as like the more energy it took to push a ball to the top of a hill. So the more energy it took, the longer it probably took, so the slower the reaction is. And the smaller the activation energy, the faster the reaction. So those are all things that I think you should know, be able to read these and figure out like what the different aspects of it are telling you. Okay. That is chapter 6. Chapter 7 is alkenes. Be able to give the complete name for an alkene. So complete is important. I mean, I don't know if your questions will come up, but if you have to write in a name for something and say you're given something like this. I don't know, I'll just put the substituent there, but like you have to both name, like give the numbers for it and like put also the substituents down and like the parent name and all that, but you also have to identify the stereochemistry at the double bond. So if you don't put that, you're not giving the complete name, so it's not completely correct. So that's important to just keep an eye out. If there's stereochemistry for a double bond, you should probably specify it. And in terms of like numbering, you know, give the higher priority to the double bond. So like here, we give the higher priority to the right side instead of the left, even though this gives the first substituent number 4. It's something we've gone over a lot, but I'm just saying it again, like do the numbering properly, give priority to the double bond over substituents. And then the parent chain should be the one that includes all the double bonds. So I'm not going to try to come up with an example here, but like just say like, no, off the top of my head, I can't do it, but say you have like a parent chain with some double bonds, and then you have like another chain in the molecule that has more carbons, like it's a longer chain, but that doesn't include all the double bonds, then that wouldn't be the parent chain. I know that came up in one of my worksheets as a question, so you can try to find that to understand what I'm referring to, but just the parent chain that you give the name to the molecule for should include the double bonds. That's the point I'm trying to make here. And yeah, that's just naming alkanes. It's pretty much the same as alkanes besides the priority for the double bond. You should be able to identify E and Z configurations for double bonds. So both identify and draw them, or be able to. So like you might be given a double bond and you might be asked to draw like C2 butane or something. So we have two things here and we're told that it's C, so they have to be, like the two methyl groups have to be facing in the same direction. Something along these lines, maybe. Just like, or you wouldn't be given anything, you're asked to draw Z2 butane, or you're given like, I don't know, something along these lines, and you'd be asked to identify if it's E or Z or name it and just like be able to identify that. And in order to do that, you use the Conning-Gold Prelog rules we used for RNS configurations. So you cut the double bond in half and you look at both sides and identify the higher priority substituent. So on the right, there's a hydrogen here and a methyl, so that would get higher priority. And on the left, there's a propyl versus this methyl, so that gets higher priority. That's pointing down, this is pointing up, so that's E. That's just a random example I came up with. You could come up with examples like this and just identify it yourself to practice. That's a pretty good way to do it. But yeah, just be able to both draw them like this and identify them when you're given a structure. Okay, there are some stability trends for alkenes that you should know. One of them is cis versus trans, and you should know that trans is more stable than cis. That is because, like, I'll go back to butane. So this is cis. That's trans. these methyl groups are larger than they look in a skeletal structure, so like it's a carbon with 3 hydrogens, it's pretty large. So they'd probably sort of get into each other's space when they're facing in the same direction like this. Like you can see they're kind of getting close to each other. Whereas with trans, they're not as close together. In fact, they're probably not bothering each other at all. So with cis, there's steric hindrance. And then with trans, there's not steric hindrance. So the steric hindrance makes it unstable for cis versus a lack of instability for trans that makes trans more stable. And we saw this in the past with the chair conformation. So like a methyl group. A methyl group up here would interact with the hydrogens that are like 2 carbons away in the chair in a 1-free diaxial interaction. And that was also steric hindrance that made this configuration less stable than if the CH3 was on the equatorial position. But I'm just pointing out that like the steric hindrance concept is something you've seen before. So it's nothing new, just recognize that like when the methyl groups get close together or whatever other groups, like with cis, then it's not stable. Okay, so that's E and Z stability trends. There's also the trend with substituents, so number of substituents. So the more substituents the double bond has, the more stable it is. I don't really have an explanation for this trend. It's just kind of something that I'd recommend memorizing, but there's a trend with carbocation stability that follows the same pattern, so you can remember that and the reasoning for that, and it goes hand in hand with this. But just to like give you a sort of pattern, like I'm just gonna come up with a substrate, like if the double bond is here, that's tetrasubstituted because it has 1, 2, 3, 4 substituents. So that would be very stable. If it was here, it would have 3 substituents because there's 1 here, 2, 3. That would be the second most stable. I don't think I have a position with 2. Oh, I guess I can put it here. So that would have 2 substituents. That would be the next most stable, and then something with 1 substituent would be the least stable. So like the pattern is tetra is more stable than tri, which is more stable than di, which is more stable than mono substituted. And you don't really have to memorize that pattern, just know that the more substituents there are, the more stable it is. And then carbocation stability. So same pattern, the more substituents, the more stable it is. So like, I'll draw a tertiary cation. And the more substituents it has, the more stable it is because like the positive charge is electron deficient, but carbons aren't very electronegative. So they're willing to donate electrons to partially more electronegative cation because it wants electrons now. So like all 3 of these carbons here are gonna donate electrons through a dipole to the positive charge. So by giving electrons, it kind of cancels out the positive charge to make it somewhat more neutral, which makes it more stable. And the more carbons that are around, which is the more substituents there are, the more stable it is. So that's explaining that. Yeah, that's explaining that pattern. And again, that's the same pattern as with alkenes. So if you memorize one, you kind of memorize them both. And this is important in like explaining reaction mechanisms, because the more stable product is going to be the one that forms more quickly, because like if we go back to those reaction coordinate diagrams, we might have like something like this, where like it didn't take much energy to get to the transition state, and the transition state would probably be a carbocation, versus something like that, which is like it took much more energy to get to the transition state. So you could think of this as like the tertiary carbocation versus the secondary, or something like it took less energy to reach the tertiary one than the secondary one, because the tertiary was more stable. So because of that, the tertiary one is the one that forms faster, which is what leads to a product. And that's explaining Markovnikov's rule. So carbocation stability kind of explains Markovnikov's rule for some mechanisms. Not all of them, and you don't have to know the mechanism for all the reactions you've seen, but for a good portion of them it does. So yeah, that's stability, and that's getting into Markovnikov's rule. Markovnikov's rule refers to regioselectivity. So it refers to where products get added. Not the stereochemistry, that would be stereoselectivity, but regio is where they're added, where products are added. And it's generally referring to like, so Markovnikov's rule is generally referring to the more interesting, in quotes, part of the reaction. So by that I mean like either if we're adding HCl, we're talking about the chlorine, like the chlorine is what's added to the Markovnikov position. That's what we refer to. You could also say the hydrogen is added to the anti-Markovnikov position, but then you're just explaining every little detail, and that's not really necessary. That's why I'm referring to the interesting part here. Or like if you add Cl2 and water, you're referring to the water when you're referring to what adds to the Markovnikov position, because I guess that's the more interesting thing there. So yeah, that's what Markovnikov is referring to. And so Markovnikov's rule isn't always followed, like that more interesting thing is not always added to the most substituted spot. And I guess I should have written that, but guys probably know. Markovnikov is when it's added to the more substituted spot. More substituted spot. But there are some examples of anti-Markovnikov reactions, which is mainly the reaction with BH3 and alkenes. But yeah, it's not always followed, so it's not really a rule. It's better to think of the rule as being in quotations, because it can be broken depending on the reaction. And carbocation stability doesn't always explain it, but it does sometimes. So yeah. And one other thing from chapter 7 is carbocation rearrangements. And this is something that I feel is likely to come up on the test because it's kind of tricky, but it's kind of important too. So if we have a double bond here, and we have like, well, I guess I'll start with one. So if we add HCl or something, the first step would be adding that proton. And then you'd end up with a positive charge here. And this carbocation is secondary because it's bonded to 2 carbons. And this carbon up here on the top of that methyl group, that is a tertiary carbon. So this secondary carbocation is right next to a tertiary position. So it will do the carbocation rearrangement. And in this case, there's a hydrogen here, so it can do a hydride shift, which just puts the hydrogen over here, and it moves the positive charge to this tertiary spot. And then the chlorine could add to this positive charge. It'll also add to this one up here, but it will add to the rearranged cation as well and lead to a mixture of products. I'm not going to screw it. So similarly, if we had this, we're going to get the same intermediate with that positive charge here. But now there's no hydrogen on this top position, so the whole methyl group has to shift, and that's called a methyl shift. And then you get a methyl group here, which you do have to draw, like you have to draw that it moved. Otherwise, the cation wouldn't have shifted. And then the cation ends up here because now this carbon has lost a bond, so it's electron deficient. And then the chlorine could add to that cation. So you should be able to recognize when these can happen and be able to recognize like what products they'll lead to. And you should also be wary of potential tricks. So like here, if we added a proton to this, I'm just going to go ahead and draw what the intermediate would look like. Like you could have a cation here. This is secondary, and there is a tertiary carbon, but it is too far away because these shifts can only occur between neighboring carbons. So you can't just say like this hydrogen goes here and then it goes to that carbon. That doesn't happen. So basically like the rearrangement will only happen if it forms a more stable cation. So it's not going to go from secondary to secondary because that doesn't form a more stable cation. It will only go from like primary to secondary or secondary to tertiary like I've shown here. It only forms more stable cations. That's just something to be mindful of. Okay. That is chapter 7. And now chapter 8, that was alkene reactions. So you should be able to do the mechanisms and draw any intermediates for the reactions that you're expected an atom for. So I'm going to go ahead and go over them. I'm just going to draw. We use this substrate for the mechanisms for all of them. So one of them is HX addition. The first step is the nucleophile, the alkene, attacks the electrophile, this hydrogen, and X is a halogen. So X equals chlorine or bromine generally. It's just a halogen. So this forms an intermediate. We get this cation forming, and that forms because that is the tertiary cation versus secondary if it attached where this hydrogen is. And like I said with Markovnikov's rule, that's the more stable cation, it forms faster, so that's why this intermediate forms. And then the bromine comes and attacks the cation. And we get that product. So that's that mechanism. It's just the first step, attack the HX, and then the second step, form the correct cation and then attack that. Now, another mechanism we'll need to know is the addition of X2. So X2, which is just, again, halogens. So first step is a bit weird. It's sort of like a cycle forming between the alkene and one of the halogens. It's not really a nucleophile, non-electrophile in this, but it's just cycle forming. And then we end up with a sort of positive charge shared between all the free atoms within that sort of cyclic ring. And we have a negative halogen that formed when that bond broke with X2. So it's going to come and attack one of the carbons and break the bond with the halogen at that carbon. And it does this kind of from the backside from where that bond is. So that ends up leading to trans stereochemistry. So I should have written this on the last one, but HX addition leads to Markovnikov product, which you guys hopefully know. And then the addition of X2 is like there's no regioselectivity because this is the same as this, but there is stereoselectivity and it's anti because it's trans. So anti-addition, or you could say it's trans. So that's the stereochemistry of this mechanism, or at this reaction, and the mechanism explains that. Another mechanism you guys need to know is the addition of X2 and water. The first step is exactly the same as the addition of X2. And that bond breaks. And now instead of a halogen coming and attacking these bonds, it's going to be the water that comes in and attacks. And it is going to attack what would be the more stable cation if a cation formed, but like because we're saying that the cation is shared between this carbon and this carbon and the halogen, you can just say that it's attacking the most stable cation here. So that's going to be the tertiary one. So it's going to attack here. So the halogen's going to have a dash, and then again, the water attacks from the back. So it's going to be opposite stereochemistry. It's going to have a positive charge because it lost some electrons, but the negative X that formed earlier is just going to give electrons to the water. And then that's going to, those single bonds with the first X are always going to be in the back. Are you referring to like this first step here or this second step with the intermediate, or I'm talking about the water attacking from the back? Or are you just talking about the fact that I have it as dashes? the dashes, it doesn't matter because like in sp2 hybridized carbon, I'm not drawing this very well, but sp2 means like the geometry is flat. So like it's a flat molecule. So when things add to this, they can either add to the top or the bottom, and it doesn't really matter. So this could either, like the stereochemistry, you can't tell what's going to happen basically when it's a flat molecule. So this could either be dashes or I could draw it like this. I was just doing dashes because I chose to, I guess, but it could also be wedges. They should just be the same when you draw it. Neither one of them is more correct than the other. Yeah, good question, because I kind of stuck to the dashes, so that was probably confusing. But what is important is the final product here. No problem. What's important is the final product is like, because the water attacks from the back, it's going to have opposite configuration of what the halogen had in that ring. So the alcohol is on a wedge while the halogen's on a dash, or the alcohol could be a dash and the halogen a wedge. So the stereo selectivity is again anti because they're trans to each other. And there is regioselectivity here, and it's Markov-Nikov for the alcohol. So both of those are things that might be good to memorize just because they help you identify what the product is when you're given these sets of conditions. But you have to know the mechanism too, so knowing the mechanism will help you remember that anyway. And then there is one last mechanism that you're expected to know, and that is the addition of acid and water to a double bond. So the first step, the acid comes in and just gives hydrogen to the double bond, which is very similar to the addition of HX. That hydrogen went here, you form this positive charge. And then the water comes and attacks that cation. Now the water is positive, but more water can come and just take away that proton, take away the positive charge. So that's the product. It is Markov-Nikov for OH, and there's no stereoselectivity. If a mechanism ever passes through a full cation like this, it's not going to have stereoselectivity, and I'm going to move on to another slide for this. It's not going to have stereoselectivity because just like a, I'll just draw the same thing. Like this is sp2, and when it gets converted to a cation, like this carbon here is still sp2 hybridized, so it's still planar, specifically trigonal planar, but it's planar. So a planar molecule or carbon will look something like this. Like it is flat. You can hopefully kind of see how my drawing looks a bit flat. The dashes are going into the screen, the wedge is coming out, and the line is going to the right. And then it's empty p orbital. It's empty because it's positive. So like you could think of the positive charge as being both above and below. And then whatever the nucleophile is, it could be water or a halogen, will either attack from the top or the bottom. So just like with the alkene, like with the question that just came up with the dashes and wedges with the addition of X2, like when we add to the carbocation, it's going to attack from the top and the bottom. So it can lead to either a dash or a wedge. It'll probably lead to a mixture of the two. So there's no stereoselectivity due to this intermediate. Okay, so yeah, that's just explaining why there's no stereoselectivity with these carbocations. I don't know if you ask about that, but the more you know. And I suppose I can go over all the reactions you guys need to know. I'm gonna have to pull up a list of them because off the top of my head, I don't have just a mental list, but I can just go over the reactions and then point out like what you need to know, and yeah, just the notes like, is this Markov-Nikov? How is it Markov-Nikov? Is there stereoselectivity? So I'm just gonna go ahead and do that, just so you have a sort of list. So we're going to use this substrate. You could theoretically do this with any substrate, just practice doing the reactions, but I'm going to do this because it has the potential for regioselectivity. Right, so first, there are two reactions you should know for forming double bonds. If we have a halogen, so either Br or Cl or whatever, you can add a base, which could be potassium hydroxide, KOH, and then ethanol or ETOH. So the base and ethanol with a halogen will form a double bond. And you don't have to know the mechanism for this right now, but you should just know that that is one way to form a double bond. That's if you have a halogen. If you have an alcohol that you're starting with, you can add acid, which would be H2SO4, and then use some ether solvent, and 50 degrees Celsius or just heat is fine. So what's important is mainly like you have an alcohol, you're using an acid, a strong acid, and you're heating it, and that will form a double bond. Those are the two ways to form an alkene that you should know. So now going on to the reactions with an alkene. I'm going to do a bit of repetition. I'm going to do that quickly. So if we're adding HX, where X is a halogen, it's Markov-Nikov for the halogen. And that's it. There's no other selectivity. So the regio is Markov-Nikov for X here. If we add X2, it's not an X, but the two X's are trans here, so there's no regioselectivity, but the stereoselectivity is anti because they're trans to each other, and the mechanism explains this. And like the X on top could be a wedge and the one on the bottom could be a dash. It doesn't matter. All that's important is that they're anti to each other. So that's two reactions covered already. And we add X2 and water. This is, again, Markov for OH. That's the regioselectivity, and then stereo is anti because they're trans to each other. And then the addition of H3O plus is, I'll go ahead and do it. It doesn't come up very often, but in the event it does, and we've already covered it. Well, no. There is no serious selectivity, but it is Markov-Nikov for the alcohol. So Markov for OH. Okay, so that's all the ones that I've already talked about, just kind of briefly gone over. There's two other ways to form an alcohol besides that H3O plus and H2O reaction I just talked about. One of them is sporation and then reduction. So, hold up, yeah. There's two steps, and it's important to write the 1 and the 2. If you don't put the numbers there, then you're saying you're putting everything in at the same time, which is incorrect. So the product this leads to wait, no, I drew that incorrectly. The other way. So the OH is anti-Markov-Nikov, so the regioselectivity is anti-Markov for OH because it was added to the less substituted spot. And then the stereoselectivity is syn or cis because the H that we added is cis to the alcohol we just added. So that can be explained by the mechanism, which you don't have to know the full mechanism. You don't even really have to know what I'm going to show you, but it explains part of why this happens. I'll go over it briefly. An intermediate that forms looks something like this. So this BH2 and the H here are basically the BH free that we added, and it forms a sort of cyclic intermediate. And the BH2 goes down here because it is just like a methyl group, kind of large. It doesn't want to get close to this methyl group here, so it stays down there. So that's the first step. And then the second step with the H2O2 and the OH minus basically just turns that BH2 into an alcohol. And because they were facing the same direction before, like the BH2 and the H, the OH and the H are facing in the same direction. And the OH got added to the anti-Markov-Nikov spot. So again, you don't have to know this intermediate, but if you can remember this picture, it might help you remember that these conditions lead to this product with those general characteristics. And the other way to form an alcohol would be oxymercuration, demercuration. So that will lead to this dash and then this wedge. So it leads to the Markov-Nikov addition of the alcohol. So Markov for OH. And then the stereoselectivity is anti because the OH and the H are added opposite to each other. Again, a mechanism you don't have to know, but I'll go over some of the intermediate steps. I'm just going to draw this one like that. So this intermediate looks very similar to like this, and then when we had this intermediate, when we added X2 in water, it ended up like the OH added to this more substituted spot. So the same thing's going to happen with water here. It adds up here. That's why it leads to the Markovnikov position. And then the second step with the NaBH4 just turns, I'll go ahead and draw the other intermediate, but it just turns the mercury into a hydrogen and it stays with the same stereoselectivity. So that's why it's trans or anti. So again, you don't have to know that, but just for your information, if it helps you remember, then that's good. Okay. So some other reactions. Oh, one thing that I should point out. There's two ways of writing this that you should know. So Br2 and H2O, Br2 is the same as X2, which I showed earlier. That's not right, my bad. So again, Markovnikov for the OH and it's anti. And if you see NBS over water, NBS is just a source of Br2. If you were to do this reaction inside of a lab, you'd more than likely use NBS because Br2 is pretty toxic and not fun to work with. So that's why NBS is common, and it would lead to the same exact reaction, I mean, same exact product, because it's the same reaction. It's just Br2 with water. So you could draw the mechanism the same exact way, just assume you're starting with Br2 that came from the NBS. Okay. Some other reactions. I'm not going in any particular order. I'm just going to try to hit most of them. If we have CH2I2 over zinc copper, that will lead to a cyclopropane. Didn't draw that very well, but it just leads to a cyclopropane like this, where the double bond was. That's all that is. There's no regioselectivity because we just added one carbon and it's attached to both. And if you wanted to, you could theoretically specify, but it kind of goes without saying. Like it's syn addition because the triangle is facing the same direction from both carbons. So stereoselectivity is syn for this reaction. Okay. Another reaction is cleavage. So there are a few ways to cleave. One is with ozone and zinc with acid. So when you have ozone in the first step and then zinc and acid in the second, you're going to cleave the double bonds. So you can draw a line through it to show that. And then because this is cyclic, it's only going to lead to one product. But if it wasn't cyclic, if it was something like this, then you'd have two different products, but you'd go about drawing the products in the same general way. And the way I do these is like I draw out a molecule as it was, and then they're double bonds, but instead of to carbons, they go to oxygens. And when you have ozone, there was a hydrogen here, there's a carbon up here on the top, but when there's ozone, it doesn't really do anything besides just add the carbonyl. So like for an alkene that doesn't have a substituent, it leads to an aldehyde if you're using ozone. But another way that we can cleave these is with KMnO4. So same substrate. So the top is a ketone here because there was a methyl group on the side. But on the bottom, instead of it being an H and an aldehyde, it's going to oxidize the hydrogen to form an alcohol. And that leads to a carboxylic acid. So KMnO4 is a strong oxidate. Yeah, it's a strong oxidizing agent, and it leads to this alcohol forming in a carboxylic acid where an aldehyde would form with ozone. So that is something that you should remember. Ozone leads to aldehydes, but KMnO4 leads to carboxylic acids if there is an end to a chain where there's a hydrogen. When we react an alkene with OSO4, which is osmium tetraoxide, and having a base is probably good, but the OSO4 is what's more important. And that OS doesn't look very good, so I'm going to try to fix that. And then the second step has NaH, SO3, and then H2O. That is going to lead to a cis alcohol, a cis 1,2-diol. So the two alcohols to get added are cis to each other, and that's the stereo selectivity, syn or cis. And then there's no retro selectivity because just like with the addition of X2, we're adding to the same thing. We can't tell which one went where. So there's no retro. So this is one way to form a 1,2-diol, and specifically a cis 1,2-diol with osmium tetraoxide. There's another way to form a 1,2-diol, and this one takes more steps. So first you have to form an epoxide. There's a couple of ways we can do this. One of them is with MCPBA and CH2Cl2. This leads to an epoxide. You don't have to know the mechanism for this. You should just know that MCPBA leads to an epoxide. Again, no retro selectivity, but you could say the stereo is syn if you want to, because it's just a ring. And then to get a diol from this, you would just add acid, I believe. I'm not seeing it on this paper, but I'm pretty sure that's all it is, just adding acid. So that will just break up this, similar to when we have like an X here, we would add water to like this carbon to break this bond, and yeah. So you don't have to know the mechanism for this, but you should know that acid will open an epoxide and form a 1,2-diol, specifically a trans 1,2-diol, because the OHs are trans to each other. So the stereo selectivity here is anti, because it's trans. And this takes multiple steps to get to the 1,2-diol. But if you wanted that stereochemistry, that's the kind of thing you'd have to go through. Another way you can get an epoxide is if you first do like X2, and water. That will lead to this reaction, this product again, the OH and the X trans to each other. And then if you add KOH and ethanol, or ETOH, that will deprotonate the oxygen and lead to it reacting with the X there in a mechanism that you don't really have to know, so I'm not going to throw it at you, but you should just know that these conditions will lead to this product. If you want me to go over the mechanism, I can, but otherwise I'm just gonna say, like, from this sort of intermediate with these conditions, it forms an epoxide. Okay. And then from there you could add acid and form the trans diol, just like we did when we formed the epoxide with MCPBA. And I think there's only one other reaction looking over this. Oh, okay, two, I guess. So if we add H2 over PDC, which is palladium catalyst, or PTO2 platinum catalyst, that will just reduce the double bond and form an alkane. And there's no regioselectivity, but if you want to be as detailed as possible, the hydrogens get added to the same side, so the stereoselectivity is syn. That's just a little detail that might come up. I don't know if it didn't come up in class, it probably won't, but that is relevant. And then one last set of reactions. I showed you guys a few ways to form a diol, so I'm just going to say diol formation. It doesn't matter which one you choose. Like starting with a double bond, you can form a 1,2 diol. And then when you react a 1,2 diol with HiO4 and water, that's going to cleave the bond between the two alcohols, just like it would cleave an alkene. And it's going to cleave it in the same exact way that ozone would cleave if there was a double bond there. So it's going to form an aldehyde, just like ozone cleavage led to. So yeah, HiO4 cleaves similarly to ozone. Okay. I know that was a lot, I'm sorry, but there's a lot of reactions. I'm just trying to cover everything. So that's chapter 8. And chapter 9 is the last chapter that's going to be on the test. That's alkynes. You should know how to name them, and the naming rules are exactly the same as with alkenes. Give priority numbering to the triple bonds over substituents. And all those other rules I talked about before. And you should know the reactions for preparing alkynes, which are pretty much the same as for alkenes. So like, if we have like 2 Cls here, we can add 2 equivalents of KOH and ethanol. So one of those equivalents will react with the halogen to form a double bond, and then the second, I can't draw it like that. I guess I can draw the intermediate. So the first one will react with one of them, it doesn't matter which. That's after one equivalent, and then after the second equivalent, it will form a triple bond and get rid of that chlorine. So like if you started with a double bond and you were asked to get to a triple bond, you would just add X2, and that would lead to this up here, and then you'd add two equivalents of base, and that would give you a triple bond. You could probably do the same thing with alcohols, just like if you had two alcohols instead of chlorines here, add two equivalents of H2SO4. Just it's the same reaction, just you have two instead of one of the thing, so you're forming a triple bond instead of a double bond. You should be able to recognize when an alkyne is terminal and when it's internal. So, for example, this version of butane is internal with the double bond because with the triple bonds, because the triple bond is within the chain, as opposed to this version of butane because the triple bond is at the end of a chain. Or you could also think of it as like if the triple bond has a hydrogen on one of the carbons, which it does here, then it's terminal. Whereas for internal, there are no hydrogens in the triple bond. So either way of looking at it works, but you should be able to identify this. And like I said at the beginning, for internal, both sides of the triple bond are secondary because they're bonded to two other carbons, while for terminal, the left side is primary, right side is secondary here. So for terminal, there can be regioselectivity if the reaction has it. Whereas for internal, there's no regioselectivity because both sides are the same. Okay. So yeah, that's just identifying these, which isn't too bad, and recognizing what that entails, the regioselectivity or the lack of regioselectivity. And now I'll just go over that same pattern, not pattern, but like with all the triple bond reactions. I'm just going to go over them and sort of explain some parallels between alkynes and alkenes. That will hopefully help you to memorize this, because you'll see that a lot of the things are very similar. So I'm going to start with this as the substrate to butane. I already talked about the ways to form it from the dihalide, so I'm not going to talk about that. But, okay, so one reaction we could do is like X2 with CH2, Cl2. That will, well, if it's just one equivalent, then it will lead to this. So I guess I'll just specify one equivalent. So you can see like there's no regioselectivity because we added two of the same thing, and it's also internal. But the halogens were added trans to each other, so this is a trans alkene or E. So because it's an E alkene, the stereochemistry is anti for this reaction. If we added two equivalents of X2, then you'd end up with an alkane, and I'm not looking at halogen. I'm not looking at chlorine. So there's no stereochemistry now because this isn't chiral and this isn't chiral, so it doesn't really matter. So there's just two X's on both of the carbons. So like looking at the number of equivalents you're asked to use is important to determine if you're drawing this alkene or the alkane. That's a pattern that'll come up with the other reactions. When we add one equivalent of HX, which is like HCl or HBr, doesn't really matter where the hydrogen and where the halogen go because, again, there's no regioselectivity, and it doesn't have to be trans, or like the stereochemistry is irrelevant. You can't tell which side it's going to attach to. So one equivalent of HX just leads to the halogen adding wherever. And then if you add a second equivalent of HX, it's just going to form an alkane, and it's going to add the halogen to the same position it did before. But again, like which position it chose, you can't tell just by looking at it, so it would probably lead to a mixture of both. Okay. I wasn't really pointing out the patterns, so I guess I'll go back since I didn't really think about that. So actually, you can't tell with this, but with the addition of X2, it was leading to the trans product just like it did with alkenes. So I'm just pointing out like that's a pattern. If you recognize that the stereochemistry is anti for X2 with an alkene, then you should remember that it's the same with an alkyne. Like it's the same general characteristic. If we have an alkyne and we react it with Li over NH3, that will lead to a trans alkene. So the hydrogens get attached to opposite sides, and like this is higher priority on the left, this on the right. So this is E or trans. So this set of conditions leads to a trans product. It reduces to triple bonds, but not all the way to single bonds. And then another way to reduce it to a double bond, that's to form the cis product, is with H2 and Lindlar's catalyst. So now both of these are pointing up, so it is C or cis. So H2 and Lindlar's catalyst leads to a cis alkene, while Li over NH3 leads to a trans alkene from an alkyne. And if we add H2 over one of those same catalysts we were looking at before, that's not quite right, or the platinum catalyst, it just leads to an alkane, so it reduces it all the way if you add H2 over the palladium or platinum catalyst. And then there is cleavage. So we can cleave either with KMnO4 or ozone, and it's just one step, and both of them will do it the same way. So it again leads to a carbonyl, and I guess I can draw it. Like it leads to two of these, but you could theoretically look at it like this, because this is like where the bond, the triple bond was, and that's where the bond was broken and the alcohols were added. So just know that like when we're cleaving a triple bond, it doesn't matter what reagent we use, both of them will lead to carboxylic acid because it just fully oxidizes it. So unlike with alkenes, this is something that's a bit different. But you could remember that KMNO4 does the same thing with both of them, I suppose. Okay. Getting close to the end. So these conditions will lead to hydration of the triple bond. And like you all pointed out earlier, there is an intermediate, which I now have. It forms an enol as an intermediate. So this is an enol intermediate. And it's called an enol because like ene is for alkene with the double bond, and then ol because alcohol. So that's where the name comes from. It might be good to know that this intermediate forms, but what's really important is just knowing what the final product is, which is a carbonyl being added. And it could either be here or here, like because this is internal, there's no regioselectivity. So it's going to add to both sides of the triple bond. In this case, both sides are exactly the same. If we just flip this molecule on the left, it looks like that. But if it wasn't the same, then you get a mixture of products. And normally these two sets of conditions wouldn't lead to the same product, or not normally, but like with terminal, they don't. But when it's internal, there's no regioselectivity. So both of these conditions will just lead to a ketone because no regioselectivity. And these conditions are exactly the same as the conditions we used for adding an alcohol to an alkene to the anti-Markovnikov position, which is important for terminal alkynes that I'm going to cover next. So I'm just going to use this substrate for the terminal alkynes. This is terminal, it's at the end of the chain. So if we do this reaction with H2SO4, H2O, and HgSO4, that is going to lead to that enol intermediate again. I'm not going to draw it, but it does form. I'm going to add one more carbon actually, because that would have looked wrong otherwise. So when it's terminal, like I pointed out before, the left side is primary, the right side is secondary. So there's a potential for regioselectivity with Markovnikov's rule. And here it shows up. So the regioselectivity is Markovnikov for the O for the carbonyl. Get added to the secondary position and it forms a methyl ketone. And while this isn't the same conditions as with the alkenes, you might recall that like again, not the same conditions, but what is the same is the mercury in both of them. So if you can remember that the mercury in both of these reactions, this with HgSO4 with alkynes, leads to the Markovnikov carbonyl, and then with alkenes, the Hg, OAC, and water, like all that, that led to the Markovnikov alcohol. So just remember that mercury, I butchered that, mercury leads to Markovnikov. So if you can remember that, it might help you remember these conditions and like what they lead to, differentiating between things. So that's just a sort of pattern between alkynes and alkenes. Similarly, we have these conditions with BH3 and H2O2, and this will, instead of adding the carbonyl on the more substituted spot, it adds to the less substituted. Put that on the wrong carbon. It adds to the less substituted spot, the primary spot. So it forms an aldehyde because that's where the carbonyl went. So the regio selectivity is anti-Markovnikov. And just like with alkenes, like if we used the same exact conditions in this case, it led to the anti-Markovnikov addition of the alcohol, so down here. So again, like just like with the mercury, when we're hydrating the double bond or the triple bond with BH3, either the alcohol or the ketone get added to the anti-Markovnikov position. So if you can remember the pattern for one of them, then you remember it for both of them. It just helps cut down on what you have to memorize. Great. Adding HX. Just say one equivalent. Will lead to the X being added. I'm not going to draw like this actually. It will lead to the halogen being added over here and the hydrogen being on the anti-Markovnikov. So in terms of regioselectivity, it's Markovnikov for X. And this is exactly the same as with alkenes. When we added HX, it was Markovnikov for the halogen. So again, if you remember it with the alkenes, it's the same exact thing with the alkynes. And if we added another equivalent, it would add the second. So I'll just say second equivalent. It'll just add another halogen to that Markovnikov position. Okay, and the addition of X2 is exactly the same as with an internal alkyne. It just forms a trans product. So I'm gonna kind of skip over that, but just like know that it's the same pattern. But in terms of cleavage, again, like both of these conditions will cleave it the same way. So we're cleaving this bond here. One thing that's going to form is the carboxylic acid with free carbons, and then on the left side, this carbon with the hydrogen. Just like when we, like if we cleaved this double bond with KMNO4, that would fully oxidize the carbon on the left here with its two hydrogens. So similarly, this carbon here, because like we're forming a carboxylic acid, it's gonna form carbon dioxide as a byproduct, just like KMNO4 with this alkene would form carbon dioxide as a byproduct. So that's just another similarity, like both conditions lead to carboxylic acids, and if it's internal, if it's a terminal alkyne, it'll form carbon dioxide. Okay. Then one last reaction. I'll just put R, X. R is just some alkyl chain and X is a halogen. So the first step with the NH2, that just deprotonates the carbon here. So it forms a carbanion. That's step one. And then step two is just adding whatever that alkyl chain is to the carbon here. So it forms a new carbon-carbon bond. And I have some examples of that on the worksheet we went over at the beginning of today. So there's that. That's pretty much all the alkyne reactions. One last note, I guess I want to make before it ends this. When we're doing that, okay, so that last reaction I just went over, this is an acetylide anion. And then that reacts with an alkyl halide, which is what Rx is. So when you're doing those reactions with acetylide anions, yes, I'll put this. It can only be done at terminal alkynes. So only with terminal alkynes. And that's because like there's a hydrogen on this carbon here, and what that reaction is doing is it's deprotonating the carbon there by taking away the hydrogen. But if we're looking at an internal alkyne, neither side of the triple bond has a hydrogen to take away, so it can't be deprotonated and you can't do that reaction, so it just doesn't work. So like theoretically, if you were given, that's not right, if you were given like an internal alkyne in these conditions, I would say that you should write no reaction. I really don't think he's going to do that to you, but in the event it did, like nothing would happen because it can't deprotonate this alkyne. So you write NR for no reaction. So that's one thing. And okay, I don't think that note is super important, but when you're doing these reactions like I had on number 4 on my last worksheet, you should always count your carbons. So I'm just gonna put 1 and then I'm not gonna write the reagents, but you should know what they are. And then so he might give you something like this. So you should count the carbons you're adding, which is 4 total. That's not right. So just like I'm going over this quickly, but count your carbons when you're doing these reactions. So you started with 4 carbons here, you added 4 carbons. So you should end up with 8 total in the end, which we did because I made sure to count the carbons as I added them. I know that seems really simple and kind of pointless, but just it's really easy to miscount. Like a lot of people, I think, count the triple bond as 1 carbon, so then they add like 1 too little or 1 too many or something. So just make sure to count them when you're done drawing, because that's an easy mistake to make. I believe that's everything I have to cover. Just that's pretty much everything that will be covered on your test. If you're struggling with anything, practice. If you're having trouble with a practice problem, you can email me or your professor. And flashcards help with memorization, so you can do that if you're trying to learn the reactions. Unless you guys have any questions for me, I think that's it. And thank you for sitting here and listening to me ramble for 2 hours. Yeah, that's all I have, I guess. So good luck studying and stay healthy. I will catch you guys next week.